Hi, welcome to exponential functions y equals a to the x and y equals e to the x. These are the generic forms of exponential equations that we'll be working with, and the primary goal of this lesson is to familiarize you with the format of how exponential functions work and how to graph them and how to look at them, and introduce this number e to you as well. So we're going to get into this. The exponential function y equals a to the x has a base a, and that's going to have implications for us. Obviously, if we put in a number like, and you can see in the chart here, like 2, 3, 4, 5, etc., and it'll make your exponential function grow or decay based on the inputs given. And we only see in those examples down below what is given as growth inputs. So if a is greater than 0, so we're just going to say a is greater than 1, then the exponential function will grow from left to right. So its slope will become steeper as it gets closer to positive infinity, is another way to say that. If a is between 0 and 1, the exponential function will decay. So the exponential functions were made to represent these large outputs, and you can see in this chart below that the base of the equation is going to define that. So there's not really a parent function here. There's going to be any number of bases we could use. And what I'd like you to do is fill this out. You should be able to get all of these within reason. You shouldn't have to do any heavy calculations. Might be a little tricky to get 9 there, but see if you can fill this out, and if you do need to end up using a calculator, then that would help. These are just numbers that you could see regularly, so do your best to have this filled out, and you never know when you'll be able to use this. So we also want to consider, imagine that we took the reciprocal of the x value in the above chart. So instead we had like our x was 1/2 or 1/3 or 1/5. Couldn't we fill out the rest of this chart as easily? So for example, if we did 1/4 cubed for that section, for the reciprocal chart, wouldn't we end up with 1/64th? Yeah, we would. So that's an important thing to keep in mind, is this number 1/4 is between 0 and 1, so we know it's going to be a decay graph, and we know it will, obviously, as our x got bigger, which it went from 1 to 3, it'd be from 1/4 to 1/64th, the y values got smaller, so it went from 1/4 to 1/64th. So just as easy to fill out. Alright, now at the bottom here we've got the introduction of this number e. This is Euler's number, and it's approximately 2.718. And what you need to know is this number creates an exponential equation that has y values that are equal to its slope values. So the slope values at these respective x values, if we match them up, so at 1 here, if we take a look here, at 1 we've got obviously a y value of 2.718 or 2.72, and the line that is tangent to, which tangent just means touching, So like the slope at that point on the curve is 2.72, just like the y value at that point on the curve. So somehow Euler was able to create, and I don't want to get into those details, but somehow Euler was able to create or find the exponential equation where the y values are equal to the slope values on this graph. And that's why this is so important. This represents continuous growth. And that's something we like to see with certain representations. And we'll see some applications of that later on in the unit. Now, moving on to graphing. So you might have forgotten this, you might remember it. If C is positive, then we're going to move, we're going to shift right. We're going to shift our, this is an exponential equation with base A. But we're going to shift everything right if C is positive. Remember, we start off with C being negative in the transformation format. So if C is negative, we have a double negative and it looks like a positive, and we shift left. And D is more straightforward. If D is positive, then we shift up. If D is negative, we shift down. So we're going to shift all these y values down. Right. So not only does base A, sorry, why did I do that? This is the base. I got so excited to see it looking at the base. B for base. Right. So A, you might remember, contributes to vertical stretch. Can't spell. And vertical shrink. And I'm trying out some new technology here, which you all probably have noticed. So there's a little bit of a delay. But anyway, so there's our vertical stretch. Cool. And vertical shrink. And another thing that contributes to is the reflection. Across, I can't spell, across the x-axis. So if A is negative, then you're going to have a reflection of the y values across the x-axis. Right, so the practice problems that we're going to look at, there's 3 of them, and you're not going to have too many questions for homework here, just because there's so much to unpack with just these 3 types. The first one is given a parent function, the parent base and a description of the transformations of the exponential function, identify the equation of the function. So we're given that this function has a base 3, and we're told that it's right 2. It shrinks vertically by a factor of 2 and down 1. Now, shrinking vertically by a factor of 2, if it shrinks by a factor of 2, that means we're going to use a fraction. So I wanted to include some different wording in here. You could say it stretches vertically by a factor of 1/2, and that would work as well. So if it shrinks vertically by a factor of 2, you're not going to multiply the y values by 2, you're going to multiply them by 1/2. And we're moving this whole function right 2 and down 1. So right 2 and down 1 are a little bit easy here in this situation. So there we have it. We have the equation of the function, the exponential function. So the second question in this list is given a parent point a parent base, a parent point, and the description of the transformations on the exponential function determine the xy coordinates of the parent point after the transformation. So we're basically tracking to see where this parent point ended up after transformations acted on it. So if the parent point of this function is at 1/4, then we should be able to follow where it goes. And just for the sake of knowing, I want to go ahead and put in the transformed parent equation. So I've got a -3 out in front raised to the x, it's left 3, so +3 power. And then if I go up 1, I go +1. Right. And that means I can track the parent point if I just follow order of operations that are happening within the equation we're given. Let me stretch this out a little bit so we're not so confused about the -3 there. The first thing we're going to do is we're going to go left 3 because the exponential, and thankfully I've got my transformations listed in order here. And maybe that could be another question, is list the order of these transformations that they should occur in. And there is a specific order because we have to follow order of operations. And x plus 3 is in our exponent, so we do that first. So if that's true, then I move my x values left 3. So my x value, 1, goes to -2. And then I stretch by a factor of 3 and negate it. So I'm going to do these two steps at once because they're just represented by one number, -3. And that's going to make my y value -3/4 because stretching vertically doesn't affect the -2x value. And then going up 1, that's going to affect my y values. So I'm going to add 1 to my y value, -3/4. So this is our final answer. We end up at -2/1/4. So after all that shifting, we actually end up at the same y value, just a different x value. And that's because we moved left 3, we've turned this thing upside down, and we've reflected across the x-axis. Well, that was reflecting upside down. But there you have it. And then, given a transformed graph and parent graph, determine the equation of the transformed exponential function. So here we've got a graph that is, the red one is the parent function, and you can see a feature that we haven't talked a lot about on these parent functions is that they always go through, when x equals 0, they always go through 1. So that's definitely a characteristic of these parent functions for exponential equations. And they're going to have a horizontal asymptote at y equals 0. So at the x-axis, that's where you're going to have your parent's horizontal asymptote, which is just the line that the exponential equation doesn't cross. However, when it's transformed, that point at 0, 1 gets moved, and the horizontal asymptote gets moved as well. So if you have forgotten about exponential equations, know that that's always true in exponential graphs. That's always going to be true. So we need to determine the equation of this, and some of the easiest way is to find out where is this point at 0, 1 going, where's the horizontal asymptote on the new equation, and not only that, but what's happening at 1 on the parent function. So here's 1. What y value are we going through? We're going through 5. So if we're going through 0, 1 and 1, 5, that means our parent is going to be y equals 5 to the x. And the transformed one is going to be something y equals 5 to the x, and maybe it has a reflection in there, which it looks like it does. So we'll know we'll have a negative there. Does it look like it's stretched out anymore? Well, we're not quite sure. We do know that the horizontal asymptote is going to be at positive 3. So we've definitely shifted this thing up 3 and then reflected it. But it doesn't look like it's been stretched at all, because I'm going to notice that there is a point at negative 4, 2 that used to look like the point at 0, 1. Well, that is the point at 0, 1, just transformed. And I can see that my graph, after finding a couple more points on here, that my graph hasn't been stretched at all. If it was stretched, then I couldn't find 2 points that were in the exact same locations, but just reflected and transformed. So that means I have no stretch, so my a value is just going to be 1, but it is going to be reflected. So I am going to have a negative 1 there. But all my points were moved left 4. So this is going to be x plus 4. So if we were going to follow the order of operations again, I would move this point left 4. And then I would reflect it across the x-axis. So it would go there, reflected it, and then I would shift it up 3. So 1, 2, 3. And it would end up there. So I know that this transformation is true because I can do that with all the points. And if you want to go through and be detailed like that, then you can. But this serves as a reminder for transformations, and thanks for watching, and I'll see you guys later. Bye.